Only this percentage of people who watch are subscribed, so subscribe now and never miss out. Enjoy the video. In our Amargasaurus episode, we looked at what was at the time the most recent research into what would have been covering those wacky neck spines. This was a 2007 paper by Schwartz et al. Who concluded that the upper portion of the neck spines, at least, would have been encased in horn. 2022 has come along, and workers have called that into question. Cerda et al. Sampled slices from 5 of Amargasaurus's neck vertebrae and some dorsal vertebrae, as well as one sample from a undeterminate Dicraeosaurid, also from La Amarga Formation, and they looked at the histology of the bones under microscopes to try and find patterns in how these bones grew, to try and figure out what are they covered in. Cerda et al. Found that the evidence for a horny sheath is ambiguous at best, but the evidence for modeling in the spines is pretty good, as is the evidence for a system of ligaments in between the spines. They also looked at the biomechanical implications of any of this and found that ligaments make a bit more sense than horns. When we're trying to infer soft tissues based on bones, we look for what are called osteological correlates. Doing this for Amargasaurus is somewhat fraught because the spines are incredibly variable. Like, between different spines, you see very different structures, and even within the same spine, the cross-section is different, the texture is different, the internal histology is different. On top of that, between breakdown after death, erosion of the fossil, and damage during preparation of the specimen, there's relatively little to work from as far as the living surface texture of the bone being preserved. So with that caveat that the soft tissues are difficult to infer, the authors noted that there are no longitudinal grooves on the surface, like what we would expect if there was a horn sheath, because they need room for blood vessels and nerves to run through. There are no rough areas where the little spikes of bone are running at diagonal angles, like we would expect, and there's no ridge or groove where the horn stops and the skin starts, which we would also expect to find. Schwartz et al.'s evidence of horns was mainly the overall shape of the neural spines, as well as this ripple and striation pattern going along them that resembles what we see in living animals with horns, bovids and so forth. But Cerda et al., having looked inside the bones, determined that, for the neck spines at least, those ripples are a result of the bone breaking down after death. On the spines over the torso, the ripples were apparently there in life, but they're patchy and they're much more shallow and spread out than we would expect a horn correlate to be anyway. And again, the neck spines are highly variable, so what texture we have varies between smooth and rough but irregular, and that's only in the patches where the living texture is even preserved. Well, what do we have? We have microtraces in the bone. There are these little lines that are the traces left by collagen fibers that had penetrated the bone. These are called Sharpie's fibers. They used to be called claviculi di Gagliari, but we can't have fun with anatomical terms anymore. But these are kind of like roots that the membrane around the bone puts into it and into whatever it's binding to. It allows it to have a strong connection to the tissues around it, but not in like a brittle way. Like there's still some give. Sharpie's fibers can attach to horn, but they could also be attaching to muscle or to ligaments or even to skin. Cerda et al. Think that horn is unlikely, partly because we don't have other strong correlates, as I already mentioned, but partly because there's evidence of modeling in these spines. As Amargasaurus grew, its neck spines changed shape. We know this partially because the neck spines contain a lot more fibrolamellar bone than the torso spines did. This is that spongy bone that's faster growing than normal lamellar bone. It contains pockets where it actually grew around existing blood vessels. So we talked a second ago about how there's no blood vessels on the surface of the bone, they're inside it. But when bone is resorbed and laid down again, that leaves a line, it's called a reversal line, inside the bone, where you can see where it stopped being resorbed and started being deposited again. And we find these lines in the neck spines on the inside, and on the 10th one on the outside as well, which tells us that as Amargasaurus grew up, its horns were changing shape. Keratin cannot change shape. Keratin, horn coverings, is dead. It can only grow outward from the living core. So there are ways that keratin could maybe reshape as the horn core changed. Maybe it was eroded off, maybe it shed its horns, maybe the horns were made up of multiple plates that like rejiggered themselves. Mark Witton has written about this with regard to Triceratops, but I don't know to what extent any of that can apply to Amargasaurus, because obviously we only have the one specimen of Amargasaurus, whereas we have a complete ontogenetic series, well, a pretty complete ontogenetic series for Triceratops. But the simplest answer is to just think, oh, they just don't have horns, and that's the conclusion that Cerda et al. Come to. In addition to the reversal lines, we also have lines of arrested growth, where the animal's yearly growth stopped and started as nutrient availability changed, and those are usually used to estimate the animal's age. What's interesting about Amargasaurus is they already measured this in a limb bone and then in a rib, and in the rib they got 10 years old, in the limb bone they got less than that, but then the neck spine shows 14 years. So this doesn't have any bearing on how we reconstruct the animal, but it appears to have been 14 when it died. Another quirk of the modeling of these spines is that the density of the spines is different in different portions. At the front of the bone, the osteons are quite dense. Sometimes this spreads into the sides, but never the back. The back is less dense. That implies that habitually the forces acting on the spine were placing the front of it under compression and pulling the back into tension. The spine was being pulled forward, effectively. That's the opposite of what we would expect if, these raked back spines were just sitting there in a horn sheath. You'd think gravity would be pulling them back, if anything. But if the spines were connected together, that would imply that the weight of the head and neck was pulling them forward, especially if, as with Dicraeosaurids, this animal was habitually holding its head straight out, slightly down, because it's a low browser. What then is holding these spines together? Well, that's the interspinous ligament. We're going back to the Sharpey's fibers again. You see, the Sharpey's fibers can't tell us exactly what they correlate to, but their distribution can give us hints. The Sharpey's fibers either only occur or occur most densely on the sides of the spines, not the front or the back. They occur not just clustered towards the bottom and not just towards the top. They're across the entire length of the spines. They are oriented kind of all over the place, but broadly forwards and backwards, diagonally to the surface of the bone. All of that implies that they were supporting a sheet or maybe a web of ligaments in between each of the spines. We talked about in the episode that in Dicraeosaurus we see these really clear ligament scars at the tops of their spines that were supporting the supraspinous ligaments, because they're paired. Then in between the forked spines, in the middle of the trough, there's this knob in Dicraeosaurus that is what the interspinous ligament attaches to. Amargasaurus doesn't have either of those osteological correlates. Schwartz et al. Thought that the supraspinous ligament in Amargasaurus was either completely reduced or just integrated into the rest of the ligament system. Cerda et al. Seemed to have a solution to the mystery of the disappearing supraspinous ligament. It was spread out across the entire spine. Though it seems like having this system of ligaments covered over by the integumentary system, covered over by skin and scales, would produce a rather thicker structure than what you usually see in old-fashioned sail Amargasaurus, where it looks kind of like a bat's wing, where it's very thin and flexy and stretchy. This looks more like what we see in Spinosaurus, modern reconstructions of Spinosaurus. But as far as I know, the reconstruction of having the muscles clumped at the bottom half or bottom third in the longest spines of the neural spines, as well as having the pneumatic diverticula in the middle, is still accurate. I did see one reconstruction where somebody filled the entire space between the neck spines with diverticula, with air sacs, and the animal could like inflate them for display purposes. And I can't prove you wrong. I feel like we're coming up on a renaissance of inflatable structures in sauropods, and that's cool. But the sail, whatever form that took, seems to have had certain advantages over horns, at least in the opinion of these authors. When you apply force to a horn, especially if it's much longer than the horn core supporting it, it transfers all of that force to the point where the horn leaves off and the bone starts. So it's kind of like a lever that you can use to break the spine supporting it. So rather than protecting it, the horn sheath is actually kind of weakening the bone. This might have bearing on Bahadasaurus. Those authors had looked at how when force is applied to a horn sheath that's much longer than its core and the horn core is curved, the force is transferred down into the center of the bone. And if Bahadasaurus's internal structure of its neural spines was similar to Amargasaurus's, that might be bad. See, Amargasaurus's spines are actually pretty bad at shock absorption. What you would want to see is a lot of cancellous bone and a lot of sinuses, and Amargasaurus doesn't have a lot of either of those. So the bone wasn't very good at absorbing strain, whereas ligaments are great at absorbing strain because they're elastic. So having a sail kind of protects the neural spines better than having horns covering them would. And it might protect the animal just as well. This isn't in the paper, it's just something I was thinking about. Like, if you put yourself in the mind of a carnivore that's going after an Amargasaurus, you're approaching its neck, and is a big sail on top of the neck that much less of an obstacle than a fence of spines? I've also seen artwork where people put like eye spots or other defensive visual elements on the sail, and that looks great. Just making the animal look bigger, just having that height on its neck might be sufficient for a threat display. And at the end of the day, these are flagellocaudatans. They've got a whip tail, they've got active defenses. Maybe they don't need the passive defenses of horns on their necks. We started off talking about correlates, so you might be wondering if there was this ligament system here and it was under constant strain for the animal's entire life, why did it not leave ligament scars on the neural spines? The authors think that we might be seeing a situation like in Spinosaurids, where animals like baryonyx, where they have very short neural spines on their vertebrae, do show pronounced ligament scars, but then animals like Spinosaurus with really long neural spines don't. It's because the strain is spread out along the entire length of the neural spine, so there's not enough force at any one location to produce a bony scar. You will note that we are now making inferences based on inferences, like we're playing comparative anatomy telephone. Amargasaurus is so odd. No living animal has anything approaching these kinds of forked neural spines on its neck, so if we want to apply what we know about living animals to Amargasaurus, we have to make multiple extrapolations. So we're kind of forced to use other fossil animals, but what we know about them is not necessarily reflective of reality, it's just a best guess. But measuring the microstructure of their bones is a good place to start. These authors have mentioned that we really need to do quantitative analysis, like finite element analysis or something, to check the various reconstructions of the neck in a mechanical context to see, well, if you apply these forces to these spines, how do they act if they're connected by ligaments? How do they act if they're sheathed in horn? Until that work gets done, it appears that the sails, whatever form they took, are back. And I want to thank you guys for watching this Your Dinosaurs Are Wrong update. Please remember to like, comment, and subscribe, and we will see you next time. We would like to extend a special thank you to these individuals who have gone above and beyond to support this show. We could not have done it without you. Thank you.